This is level 2 of the CFA program, Quantitative Methods, and the reading on big data projects. As you look at the learning outcome statements, I want you to focus on the first 4. Data analysis project, preparing and wrangling data, data exploration, model training, and notice those action words are, pretty much describe. There's one explain in there. As I'm reading those, I'm thinking that those could be learning outcome statements for almost anything inside of this big data topic. I mean, it could be for medicine, it could be for engineering, but look at the 5th one there. Describe preparing, wrangling, and exploring data-based data for financial forecasting. So in my mind, these first 4 learning outcome statements are preparing us to be able to attack that 5th one, because that's the most likely kinds of a question that you'll get on the exam. I mean, I can't imagine that remember, you're going to get a vignette. I can't imagine the vignette would say, hey, there are a bunch of engineers who are hoping to build a bridge across the Atlantic Ocean, and they're consulting you for this big data project. So, of course, it's going to be couched in the terms that sound like this. Let's determine whether or not a firm is going to pay a dividend. Let's try to figure out whether or not a bond is going to default. Let's try to figure out whether or not cash flows or revenues are going to increase or decrease. So financial forecasting. So what we need to do here is spend some substantial time trying to figure out let me just go back here. What is a big data project, from an elemental level, and then we need to apply it. You probably remember that back in level 1, there was just one reading on big data. And so here's just a quick summary of this. Boy, data is significant, fast, and complex. Wow. And look at the illustration there. There are these 3 V's. So data volume, of course, that means quantity of data. Data variety means that you have a bunch of different sources. Data velocity means the speed with which that data is created. And one interesting thing about the beginning of this reading is that it adds a 4th V, veracity, which is credibility and reliability of data. And so that's what we're doing back here. Like if you look at these first 4 steps, or actually 2, 3, and 4, those learning outcome statements, preparing and wrangling, data exploration, model training, we're trying to figure out, is this model credible, and is it reliable? Now you should remember from level 1 and also from our previous reading that there are 2 types of data. Structured data can be arranged neatly in a data table. So just think of a big old Excel spreadsheet where you can have things like operating cash flow, free cash flow, size of the dividend, expenses, all that kind of stuff, right? And then unstructured data, boy, this is just a whole bunch of stuff that you need a special program for to, kind of force them into columns and rows. And of course, the example there is social media, and we'll talk about that as we get through this slide deck. All right, so let's start with that first learning objective. State and explain steps in a data analysis project. All right, so what we're going to do here in this slide is look at traditional big data or structured big data. So this is what we've done before. In fact, this is a part of the initial quantitative methods back in level 1, and then also in levels 2 and 3. Just think of regression analysis here. I mean, that's probably an okay, even though it's not limited to that, but just think of it in that context. So conceptualization of the modeling task. So define the problem. And let's go back to that example that I gave you in the previous recording about your supervisor comes and says to you, hey, I want to know if this particular firm is going to increase or decrease its dividend next week at the board of director meeting. So define the problem. So the problem then is dividends. Ultimately, but what are all of the input variables that will affect whether or not the board decides to increase its dividend, keep it the same, or decrease this dividend. So look at that. The second part in there, establish the model output, how and who will use the model, and how it will be incorporated. So we need to figure out exactly all those inputs, right? And then we've got to say, all right, which one of us inside of our working group is going to be responsible for each one of those? You might have somebody in charge of revenues, you might have someone in charge of expenses, you might have someone in charge of, evaluating the personality of the board, and then how we're going to use this model, how we're going to then present it to our supervisor. And then the second step there, data collection. So we have all these individual tasks, and then we need to figure out, all right, how are we going to collect this data? We're going to do it inside of that particular firm, and then we've got to go outside to all of the external sources. Data preparation and wrangling. Wrangling just means that we're going to, wrangle. We're going to try to figure out what do we need and what don't we need. I tell my students all the time when they say, Jim, you gave us 4 pieces of information in this question and we didn't need it. And I say, precisely. Of course, your supervisor is going to give you a task and say, here, go figure this out. And they're not going to say, oh, ignore that stuff over there and concentrate on here. Data exploration. We'll spend a lot of time in the next few minutes on explanatory data analysis, selection, and engineering. And then, of course, this is the idea of machine learning and big data we need to train. So we have this model, right? And then we press a button and it does a bunch of stuff. And then we evaluate the output, and then we maneuver and we switch and we transform and we do a bunch of stuff so that we can train the model. Now, of course, the steps are going to be, how about if I say virtually identical for unstructured data, because the goal is still the same, to try to determine whether or not a firm is going to increase its dividend or not. But if we're looking at unstructured data, if we're looking at text or textual data, then we need to modify all the stuff that we did in that previous slide to include things like text problem formulation, text curation, text preparation and wrangling, and text exploration. And so think about what that means. So imagine that I'm Jim, right? I'm Jim, and after all, I do have a PhD. I do hold the CFA designation. I have published articles and books, right? So let's suppose that I have some kind of a social media footprint out there in which every day I'm publishing stuff about dividends. And so in those, in my social media, I use words like free cash flow, and I use words like revenue enhancements, and I use words like board of directors attitude towards dividends. And I do this with text, I do this with pictures, I do this with whatever else is out there in social media. I'm not a social media person, but I know there's a lot of stuff out there. And so what we need to do is make certain that we can take all the relevant stuff that I'm publishing and then put it in some kind of some kind of a structured format. So notice the third purple row there, text preparation and wrangling. So cleanse and pre-process the unstructured data into a format that is usable by traditional modeling methods. Moving on to the next learning outcome statement, describe objectives, steps, and examples of preparing and wrangling the data. All right, remember that preparing and wrangling of the data, think about wrangling of the data as kind of pre-processing. And pre-processing, what are we going to be faced with? We're going to be faced with, some outliers. We're going to be faced with redundant variables and maybe irrelevant variables. And so what we want to do is we want to wrangle them. We want to pre-process them. Let me give you a quick example that shows up in the actual reading. Think of a data set of a wealth manager that has client information and a column, so it has a column of the name and a column for all a bunch of stuff. And then there's one column for birth date. And so you just kind of scratch your head and say, all right, what what good is a birth date? So how about if we transform that into age of the client? Well, that's probably relatively important. So think about data preparation cleansing. So raw data can be invalid, inaccurate, incomplete, or have duplicates. So we're going to inspect, pinpoint, and reduce. So here's a great exam question. The process is key as erroneous data leads to, you ready for this? Inaccurate analysis, wrong conclusions, and misleading business decisions. So it makes a lot of sense to have a vignette and then have somebody inside of the vignette make a comment that says something like, hey, we need to cleanse this data because it'll lead to erroneous data. And then you go down and question number 5 is, do you agree or disagree with that comment? And you say, yes, of course, that's all part of preparing and wrangling the data. So here's a list of some errors in this raw structured data, incompleteness error. And there are a couple of examples of tables inside of the actual reading where, you have a big old matrix and there's, just a bunch of blanks and maybe a couple of, NAs, not applicables. So what do you do with the incompleteness error? So you have valid errors, you have accuracy errors, you have consistency errors, you have uniformity errors, and duplication errors. So imagine this big old spreadsheet where you have, like throwing darts at it. Not that you want to do that to your monitor, but you throw darts, that you have all these darts on there. And so you have to think to yourself, okay, there's no way that this data set is going to give me some output that I can feel comfortable making a financial decision on because of all those arrows sticking out of the dartboard. So we need to try to pull those darts out and, maybe replace it or figure out something, transform, et cetera, et cetera. All right, so data transformation. So extracting a new variable. One of the first things that I learned in my econometrics class back in the old days was that my professor said, look, if you have two variables that you think are important, but they happen to be correlated, just use them as one variable as a ratio. Put one in the numerator, one in the denominator. And I always thought that was clever. So extracting a new variable from current variable, think ratios. Filtration, identifying and eliminating data, aggregation, selection, so conversion. So those should make sense. Identifying outliers. All right, so we know about this standard deviation. We've been talking about that since level 1, and I'm guessing that you've been talking about that since your undergraduate days. And I'm always curious about the 1 and the 2 standard deviations. I mean, we can go all the way back to, whenever our famous Russian statistician Chebyshev, came up with his little model. 1 standard deviation, 2 and 3. I always question, why can't it be 2.5 or 2.75? But anyway, the reading suggests the data value outside of 3 standard deviations is considered an outlier. That's probably a good thing to memorize. You can also do interquartile ranges, 1.5 or 3. So what do we do with these outliers, trimming or truncating? We can eliminate the highest percentages and the lowest percentages. You can do, like in Excel, you can do that data sort function. And so you're just going to chop off the top 2% and chop off the bottom 2%. I was never a big fan of eliminating data from my data sets back when I was writing my dissertation and doing research. But I did become aware of this process called Windsorization. It's kind of interesting. You pick, so instead of eliminating these, you just say, all right, I'm going to pick a maximum value, or it could even be a minimum value. But I think Windsorization, I think it was named after this dude Windsor. I think he his outliers were all high, so he picked a maximum value. So instead of having 4 million as an outlier, he picked the maximum value of 500,000 or some number. So you replace. And you can also scale. I remember when I was writing my dissertation, I needed to use a size variable for one of my independent variables, and I was getting some strange results, and my professor just looked at me and said, hey dude, why don't you just take the natural log of size? And that kind of eliminated the problem. The reading does mention a couple of scaling techniques. First of all, normalization, and then second of all, standardization. So let me skip down to standardization first of all, because this is probably something that you're way familiar with, especially back from level 1 material that we covered. Adjust the data to have a mean of 0 and a standard deviation of 1. So there's the beautiful bell-shaped curve normal distribution over there. So this is how we standardize. We take each x variable, subtract it from its, from its mean, and then divide by the standard deviation. That's why we call it standardization, because we divide by standard deviation. Now you can normalize something by taking differences as well, but both in the numerator and in the denominator. And in the denominator, you take the difference between the maximum and the minimum values. Moving on to the next LOS, describe methods, objectives, and examples of data exploration. So there are 3 critical tasks here: exploratory data analysis, feature selection, and feature engineering. This is how I want you to think about this. Exploratory data analysis is almost totally description. We're going to do things like histograms and bar charts and box plots and density plots. And we're going to view these things, right? These are visuals. We're going to look at them so that we can possibly identify relevant patterns or relationships that are visually outstanding. All right, so EDA, think of description. Then feature selection, I want you to think of reduction, right? What we're going to do is we're going to find relevant variables, and we're going to try to eliminate irrelevant variables and unneeded variables and all that stuff. And then feature engineering, I want you to think about optimization. So description, reduction, and optimization. All right, so let's look first at exploratory data analysis. So there we go, exploratory graphs, charts, and other visualizations. The objectives: acts as a communication medium among project stakeholders and analysts. So let's come up with an example here. Let's suppose, and I like my dividend example that I've used so far here and in the previous recording. So our team has been formed to come up with a model in which we're predicting whether or not a firm is going to increase its dividend. All right, so what are we doing? We have all these charts and all these pictures and all these graphs, and we're going to try to uncover a relationship, uncover a pattern. Look at that second teardrop: understanding data properties, finding patterns and relationships. So we have all this data from, where are we getting this data from? We're getting it from traditional sources, right? Like financial statements. So we'll do things like ratios and amounts, but we're also getting it from news articles, and we're getting it from social media, like me, Jim, right? That example I gave you before, I'm a social media guy, and I talk about free cash flows and dividends, right? So inspecting basic questions and hypotheses. Here's a basic question, does the composition of the board contribute to the likelihood that the firm will increase or decrease its dividend? In other words, are the individuals inside of the board, are they more or less likely to be able to say to shareholders, hey, you know what, we have all of this cash, here's a dividend? Or are they saying something like, hey, we have all this cash, let's invest it in positive net present value projects so that you shareholders don't have to pay taxes on your dividend income? So you see, we're trying to find patterns and relationships, but there's no way that the financial statements are going to be able to communicate, the attitude of the board members in regards to compensating shareholders as a dividend or reinvesting back into the company. Documenting data distributions, right? And so finally, planning the modeling strategies for the next steps. All right, so here's feature selection. So what did I call that? Reduction. Selecting only features that contribute most to the prediction variable. All right, so structured data, different columns. Parsimonious model. I remember in one of one of my papers that I wrote in graduate school, my professor said, parsimonious, Jim, parsimonious. And I had to get out my dictionary and look up, and I was like, oh, skeletal. I know what that means. So parsimonious model, most desirable outcome, maximum predictive power. And here's an important one. This is a great correct exam question. It reduces overfitting, improves the model's predictive accuracy. Feature selection is systematic and iterative. So what we're doing in this, in this machine learning of our big data is we're iterating, right? We're going over and over and over. If then, do this. So we're doing this again and again, and it's systematic. So we're concerning one variable here, then this variable here, then this variable here. And I, as the team leader, I may say, look, I think that these variables are super important, like cash flow. I think these variables are less important, like the dividend 20 years ago. And so we're going to try to figure out the relationship between and among all of those. But look at the last arrow point, right? Dimension reduction can be used to reduce a large number of features. That makes perfect sense. And then engineering, transformation or decomposition. So this is what we're going to do. We're going to do have created a new feature, or perhaps multiple features. And one-hot encoding is a really good example. Think about one-hot encoding as similar, maybe it's even identical to our dummy variables from a previous reading. But remember, in the old days, we had a dummy variable for, well, let's use my example. If the firm increases its dividend, that's a 1. If it doesn't increase its dividend, that's a 0. But here, we don't have binary stuff, so we probably have a series of variables. Let's take a quick example. Suppose we have colors like red and green and blue. So if it's red, it's a 1. If it's green and blue, it's a 0, right? And then going down there. So you can put this one-hot encoding. It's kind of like dummy variables. All right, how about objective steps and techniques in model training? All right, so we're going to do this with three steps, right? Method selection, performance evaluation, and then tuning. All right, so method selection, selecting and applying an algorithm to a machine learning model. Now, of course, we need to compare and be aware of the difference between the supervised and the unsupervised learning. So supervised machine learning models, of course, we learned this in the last recording, use labeled training data to produce a known outcome, regression analysis, support vector machines, neural networks, and then the trees, we did a cart in that last video. And then unsupervised learning, it does not have that target variable. Remember, there's no dependent variable in unsupervised learning. And so we're trying to take this big data set and we're going to do things like cluster. So we're trying to do the cluster of the circle and the cluster of the trapezoid and the cluster of the triangle. Those kind of look like those shapes, right? Dimensionality, reduction, and clustering. Types of data, numerical data, textual data, image data, speech data, right? Those make perfect sense. Size of the data, they can be 10,000 to 100,000 features. Wow. Those neural networks, they work better on longer data sets. So think about, I always think about, breadth. You guys can't see my hands all the way out there. So I'm stretching longer data sets. I'm stretching way, way out there. And then performance evaluation, we did this back in level 1, and then we did a little bit of it even in our previous recordings on quantitative methods. So we're going to measure the model's performance. I mean, that makes perfect sense. So what are we hoping for? Here's a little matrix. And interestingly enough, this is called a confusion matrix, which really, I'm not quite sure why that term is used. I'm pretty sure it used to be called a classification matrix, but who knows when they changed it to confusion matrix. But that's the term used inside of this reading, so that'll be the term that we apply as well. But note, we're looking at top left and bottom right, so true positives and true negatives. So this is the scenario under which our model correctly predicted a firm that increased its dividend and correctly predicted a firm that did not decrease its dividend, true positive and a true negative. Of course, the problems then arise when we go in the upper right corner a false negative and in the bottom left corner a false positive. And of course, as you're looking at this, you should automatically think, hey, that sounds an awful lot like type 1 and type 2 errors. And of course, that's what they are. So this is just a quick slide to summarize what I just said in that previous slide. Let's go ahead and look at some performance metrics that are calculated from the confusion matrix. All right, so 4 of these things. Precision. Notice I have in bolded red, predicted and actual. So under precision, notice what we're doing. The proportion of correctly predicted positive classes, so that's true positives in the numerator, divided by the true positives plus the false positives. So this is total predicted positive classes, and this is useful when a type 1 error is high. So remember precision, and then remember sensitivity. In the we need the total actual positive cases. So we're doing true positives in the numerator divided by true positives and false negatives, and this is when a type 2 error is high. And then accuracy, what we're going to do is we're going to do a bunch of stuff in the numerator and a bunch of stuff in the denominator. Here, these were relatively simple, right? Just type 1 and type 2 errors. Now what we're going to do is we're going to do true positives and true negatives in the numerator divided by like the total there. So that's divided by the total. Accuracy. So this equation here is pretty much the standard metric for evaluating model performance. And so think of these two here, precision and sensitivity or recall. Think of these, I mean, of course, think of them as type 1 and type 2 errors, but think of when we did, back in level 1, we did ratio analysis, right? We did things like, we did liquidity ratios and we did leverage ratios and we did operating ratios, right? And so those were 3 kind of sub groups of ratios. And then we got to the main ones. The main one was return on assets and return on equity. And so, you know, your accounting professors and back in level 1 would always make the case that return on equity, return on assets, those are super important. Those are the most important. And from those, you can worm your way back into liquidity or leverage. And that's what these are. So accuracy, this is pretty much the standard metric. However, it's not perfect. In fact, it can give some misleading performance evaluations if the classes are imbalanced. So here's the good example of an imbalanced class. Suppose we're trying to figure out whether or not a bond is going to default. And so we have a group of C-rated bonds, which have a pretty high probability of defaulting. And then we have a group of, let's say, A-rated bonds, which they may never, ever default, right? I mean, I think the default rate on A-rated bonds is, you know, I don't know, 1 or 2%, whatever that was. We did learn that at some level. So think about accuracy there. So we have the problem of imbalance. So if we don't have classes that are imbalanced, then we love to use this method. But if we have imbalanced classes like I just described, then we need to go to the F1 score. And so all we're doing here is there's a good old formula there at the bottom, and you can see that you just have to describe it. You don't have to calculate it as part of the learning outcome. But notice the second purple teardrop point, more appropriate than accuracy when there is a class imbalance. So that sounds to me like a classic exam question. And look at the third teardrop point. Higher the F1 score, the better is the model performance. So that's, of course, you probably should remember that. And this is really a harmonic mean of precision and recall. Harmonic mean, remember that, you know, when you're in kindergarten, right, don't you learn you can take the average, right? And when you do the average, you just add and divide by n, right? And then over time, you learn that there are other ways of trying to figure out what's in the middle. And so sooner or later, someone decided to do a harmonic mean. Do you remember that formula for harmonic mean? if I have 10 observations, you put 10 in the numerator and then you divide by the reciprocal. And so you do 1 over A and 1 over B. And so what does that take me out to J? So I have 1 over J, that's 10. So that gives me the harmonic mean. It's just another way of calculating something that's in the middle. But what's important is that class imbalance. All right, how about describe objective steps and techniques in model training? So let's do this receiver operating characteristic. And this is one of those, I bet, relatively new topics that it could be called, you already know what this is. So go back to our normal distribution days and let's go back to trying to determine the probability that an option is going to be exercised, right? So we do this thing and we compute and we estimate and we calculate the area under the curve. And that's really all we're doing here. So notice what we have on the vertical axis. So there's sensitivity and there's on the horizontal axis, specificity. And all we're doing is trying to figure out the area under the curve. So there's the AUC. And so if we're perfect over on that left green, we're perfect. So the area under the curve is 100%. So our receiver operating characteristic, what is this? It's a curve showing the trade-off between false positive rate and true positive rate for various cutoff points. So if we're perfect, then we have the green. But look at the one, next to the green one. Is that orange? So this receiver operating characteristic curve, it's upward sloping and then it curves over. And that's probably a pretty good one. Area under the curve, 75%. There's a 50% model where the 50% diagonal line, which probably doesn't give us a whole lot of value other than just flipping a coin. And then if our area under the curve is 0%, then we really stink. Another way to go ahead and evaluate a model is through this thing called a root mean squared error. We've done this before, and I'm always tempted. Now, I'm not saying for you guys to do this, but I'm always tempted to think this RMSE is just like a standard deviation. It's super similar to a standard deviation. However, you need to know the subtle difference, and I think this might help you answer an exam question. Remember, standard deviation is a measure of the variability around a mean, like the spread around a mean. But this root mean squared error term is not so much the spread as a measure of distance between the predicted and the actual. So look at that formula there. You have the predicted value versus the actual value. And of course, you're going to square it to get rid of the negative. And then another difference between this and the standard deviation. Here you divide by n, standard deviation you divide by n minus 1, which is the degrees of freedom. So that illustration over there on the right is really very clever because what it does, it tries to tell you that, okay, we're going to draw a line and what we're going to try to do is minimize the distance between each of our dots, and we're going to draw a line that represents that minimal distance, right? So small standard deviations, small root mean squared errors indicates potential better model performance. How about model tuning? We talked about this in the previous recording. We had a bias error, which was essentially an in-sample error. Variance error was an out-of-sample error. So we have this concept of underfitting and overfitting. And I just absolutely love illustrations and graphs like this, where we're comparing errors on the vertical axis. So let's call this the prediction error. How well our model predicts some kind of an outcome compared to complexity and flexibility of the model. And so, of course, the training error is downward sloping, right? If you train and train and train and train, right, sooner or later you're going to get better at it. But then we need to worry about underfitting and overfitting. And so there's that, looks like a little smile, right? The red. So this is a classic microeconomics marginal cost, marginal benefit trade-off. So look in the middle there, bias, variance, error, trade-off. And so there's a minimum point there where the slope is 0. And what we're trying to do is minimize. We're going to try to find that point where that model complexity and model flexibility is minimized. Now, how do we get to that point? Well, what we do, look at the LOS, right? techniques in model training. So let's go through this. The algorithm is then run on the data again. Output is compared to its performance using this validation set. And so what we're going to do over time, we're going to run this again and again, and we need to figure out what those hyperparameters are, the optimal hyperparameter that's going to lead to the most accurate model. Now remember, these hyperparameters are determined by us, right? We're the financial analysts, so we're going to say something like, we think the hyperparameter ought to be, 4 or 0.6 or whatever that number is. So then we run this and we run it again and we think, oh, well, maybe it should be 3.6 and not 4, or maybe it should be this. So we're trying to figure out this whole process so that we can optimize that hyperparameter. Ceiling analysis employed in case of a complex model. I think all these models are complex, right? Ceiling analysis, systematic process of assessing different components in the pipeline of model building. This goes back to what I was saying earlier. Remember, we formed our team, and I said that part of the team is in charge of revenues, part of the team is in charge of expenses, part of the team is in charge. So the team has all these individual responsibilities. Remember, we're trying to figure out whether a firm is going to increase its dividend. And so the ceiling analysis is trying to determine, what is relevant and what is not relevant inside of that pipeline. And we want to make sure that we don't go past the ceiling and we don't go below the floor. We call it ceiling analysis. Potentially improve performance by further tuning. So think about, let's suppose you're in charge of revenues. So what do? You break down revenues into each individual silo, so each individual product line. So if this is a company that does, hygiene products, so you have the toothpaste silo, and then you have the soap silo, and then you have the shampoo silo. So now you have these revenues inside of these silos, and you're trying to determine, okay, which one of these, and in fact, it's probably all of them, right? What's the percent? What's their contribution? What does the sales force look like? What kind of a marketing strategy is inside there? What is the elasticity of demand from the market? All right, so think about, we're building this model, we're building this pipeline. Do we want a big old metal pipe, or do we want, some kind of plumbing piping? What kind of piping do we need? So look at this example here at the bottom, our illustration. So we take a picture, right? We have a camera image. And so think about, there's a million pictures out there, but we're interested in the face. So we eliminate all those pictures out there that don't have faces. So now we have the face, and then we want to chop it into the forehead. Of course, some people have higher foreheads than others, right? And then the mouth, and then the chin. So we're segmenting those, right? We're trying to figure out that whole pipeline, and then we can use some kind of a traditional model. We can come up with a logistic regression, 1 for dividend increase, 0 for something else, and then we can label it. All right, so that was a series of slide decks that, although I used the example of the change in dividend, those things could be applied to almost any big data project. Remember this, this reading is called, hey, let's figure out some kind of a big data project. So now this particular LOS tells us to data for financial forecasting. So think about my example. I'm Jim, and I'm blogging, and I'm texting, and I'm tweeting, and whatever else other people do on social media about dividends, right? And I have, every day I post something, and every day I use the word free cash flow. All right, so I have free cash flow. So I have it thousands and thousands of times. So you have access to this data, so you dump it in your lap, right? And so you're thinking about, all right, I have this big old, I'm looking down at my lap, I got all this data, I have no idea what I'm doing with it. Think of Jason Bourne in that second Bourne movie. I think it was called The Bourne Supremacy. In the beginning of the movie, he has a book, and he's trying to figure out who he is. What have I done in my life? What am I doing? That's this gigantic problem, and we really have nowhere to start. So what we do is we start preparing and cleansing the data. So remove the HTML tags, remove punctuations, remove numbers, remove some kind of irrelevant spaces. We can normalize this data just like structured, and so we come up with this thing like a token. So I'm going to have, so what did I write? Free cash flow. So free is a token, cash is a token, and flow is a token. And so this pre-processing is going to identify those tokens, right? Free cash flow. And then it's going to identify when they are used together, because somewhere else in the in my social media, I could say something like, hey, my son won a free miniature golf game last night by having a hole-in-one. So there's the word free, right? That's free, but it doesn't have anything to do with free cash flow. And then somewhere else I say, my other son came to me and said, hey, Dad, I need some cash. So there's cash that shows up. Well, that doesn't have anything to do with free cash flow. And then my other son, who was an artist, comes to me and says, hey, Dad, look, I drew a zombie and here's the blood flow out of his or her eye. So I tell my audience out. So there's flow. So there's free cash flow. So what we need to do is identify those as tokens, but then we need to identify which of the tokens are important and which are not. All right, so how are we going to normalize these? So lowercasing the alphabet so that they all look the same. Remove stop words like the and are, right? That makes sense. Stemming, this is fascinating here. And lemmatization. I go back to what my dad said to me when I was in the 8th grade. He said, you know, son, when you get to college, when you get to high school, you're taking Latin. You're taking Latin. And when I got to high school, they didn't offer Latin, so I had to take German. And so I would have learned this. You know, stemming is just the process of reducing a word to its base one, its base value. Like, let's take the word cat. So you could have cat, right? That's a base. And you could have cats. And you could have cat-like, you know, like someone's out there, he's cat-like. You could have, you know, caterwailing, caterwalking, I don't know. You know, so you reduce it to cat. So that's stemming. A lemmatization reduces it to its basic form in the dictionary. Like, let's take the word walk. So I can do walk, I can do walking, I could do walked. I could do a walk through, I could do a walk around, but lemmatization, what it does is it gives you context. So the stemming just reduces the word to cat, but here it reduces the word to walk, but it also gives you a context like walk around or walk through or whatever else walk can do. So imagine this, you know, this software that's this algorithm that's able to do all this stuff. I don't know. Is there a good exam question in there called stemming and lemmatization? I don't know, but I would know the subtle difference between those two. Of course, when I got my SAT grades back when I was in the 11th grade, and my verbal score was way lower than my math score, my dad said, "See, I told you should have taken that." That has nothing to do with anything that we're talking about here. How about bag of words? This is interesting. So we're going to build this DTM, this document term matrix. So think about going back to my free cash flow. So we can have this bag of words, free cash flow in there, and then we can have revenue. So one of you was on my team and you were in charge of the silo for revenues for toothpaste. And so somehow revenue, so we have free cash flow, those are tokens, right? And you put them in the bag of words, and then toothpaste revenue, that shows up. So you got a token. Toothpaste is toothpaste. Would that be one token or two tokens? Oh my gosh, let's not worry about that. Let's just say toothpaste revenue, that's two tokens. So you put those together and you link those, and then somewhere in there you're going to have a number like, okay, revenue here for toothpaste is 10, and then free cash flow, you know, is 6. And so those are going to relate to each other over time. So look at this document term matrix. So it's probably good that you know this definition, where each row belongs to a text file and each column represents a token. And you can do n-grams, so there can be a sequence. So a 3-word sequence is a trigram. All right, how about exploratory data analysis? So term frequency, word associations, word count, average word, sentence length. So all those things, exploratory data analysis. So we're getting back to my free cash flow and revenues and board of directors and all those little pipeline things that we established, and we're trying to figure out patterns, co-occurrence of words, bar charts and word clouds. Feature selection will eliminate common words, highlight useful words. So hopefully every time I tell my audience that my son is wanting cash, hey dad, I need cash, 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 cash. I mean, that happens every day, right? So that may show up a million times. So we want to eliminate those. All right, so feature extraction. Oh boy, this is really, really cool. What we're trying to do is, this is like, let's go back to the capital asset pricing model. Remember, we learned that was a one-factor model. And then we learned about multiple factor models, remember, so we used things like value and growth and some other things. So what we're trying to do is we're trying to map textual data to these real valued vectors, or these factors. We called them factors in the old days. Now we're calling them features, so that they are relevant and that they're important inputs into our model. So the bag of words, one of the most common ways of numerically representing text, does not represent word sequences or positions. All right, so feature selection, so a subset of tokens. So this is what I was talking about with the free and the cache and the flow. What we're trying to do is make the machine learning model more efficient and less complicated, eliminate the noisy features. So we want to get rid of all those references to cache. Frequency analysis filters unnecessary tokens, of course, term frequency and document frequency. Now remember back in level 1, we did a chi-square test, and we wanted to ask the question like, are these two means the same, or are these two variances the same? So what we're trying to do, two variables in a contingency table to see if they are related. So all we're doing is we're expanding our chi-square test from means and variances to things like anything else that we've talked about. Test the independence of the occurrence of a token and the occurrence of the class. So tokens are ranked by their usefulness. And so what we want to do is we want to find the tokens that have the highest chi-square test statistic. And those will be selected as features. So clearly, free cash flow, toothpaste revenue, those are going to be features that we want included in the model. And we don't want a free miniature golf game to be included in the model. Mutual information gauges the amount of information contributed by a token to a class. Think of this as like, I hesitate to say this, so just be tempted to agree with me here. The amount of contribution, so think of it as kind of like an R squared, like it's like an individual token's R squared. It's not exactly that, but it's similar. How about when we simplify this information? So different numbers are converted into different tokens. So we can take a 5-digit number and replace it with, number 5. We can do n-grams. We can discriminate. Here's the example. Stock market is a bigram. What we want to make sure is we want to look at what those adjacent words are as a single token. There's stock market. So does that mean toothpaste revenue? Is that a bigram or a trigram, or is that one token, or is it a single token? So this n-gram will figure that out for us. Name, entity, recognition, right? CFA, so that makes sense. And then parts of speech, language, structure, and dictionaries to tag every part. So of course we want we want CFA, we want institute, and we want to make sure that they're highlighted and emphasized together. All right, how about if we evaluate the fit of a machine learning algorithm? So I really like this illustration over there on the right. So let's suppose that we take this unstructured data. So here I am, Jim. So I have all this data on my social media. All right, what we're going to do is we're going to try to put it into structured data. So we do the tokens, we do the sentences, we do all of that into our document term matrix. And then somewhere in there, we're going to choose a model to help us evaluate our new structured database. And let's go ahead and just suppose we'll choose this supervised machine learning algorithm of logistic regression analysis. So we have the training data set, then we're going to do the validation data set, and then we're going to do the testing data set. So we do that over and over again, and then we have this predicted classification. Does the firm increase its dividend or does it not? And there's a possible percentiles there on the bottom table on the left. Continuing on this LOS, method selection. So now we have a known output. We have positive or negative sentiment classes. So we're going to use supervised machine learning algorithms. We can use any one that we want, right? We did logistic regression in that previous one. So we can classify these as either positive or negative. So, right, the dividend increase, yes, the dividend stays the same or decrease, that would be a no, positive or negative. So that logistic regression employs the method of maximum likelihood estimation. We know all that from level 1 and also level 2, right? We just did this in a previous one. So suppose for some reason that we come up with this p-value of 0.9 for a particular sentence. So what did I say back in my social media? I wrote something like toothpaste revenue is going to increase by this much because I've gone out and I've surveyed my neighbors and they're all brushing their teeth more. There's a 90% probability that this sentence has a positive sentiment, which means that's going to increase the likelihood that the firm will increase its dividend. So you go from teeth brushing in my neighborhood to a dividend increase as an output of the model. Here, back to this performance evaluation using the area under the curve. We can do this and compare comparing the training data with the cross-validation data, A versus B. That's the CV data over there on the right. So training data, 96%. So I don't know, that might be good. We may accept that. But then the cross-validation exercise, that's only down to 86%. So we may or may not like that. Depends on some of our hyperparameters, depends on what we've learned over time. But then what we're going to do is we're going to try to predict the sentiments of the sentence structure using that cross-validation. We can use that lasso model that we did back in the previous example. Remember, the lasso model was one of those penalized regression models. So let me just recall quickly here. What was our regular old ordinary least squares objective? To minimize the distance between all of our data points, right? So we get that line. But now we're saying, hey, you know what? We're adding all these extra variables. We need to put a penalty in there for those extra variables. So look at that third teardrop point. The lasso penalizes the coefficients to prevent overfitting. So the penalized model only selects the tokens with statistically non-zero coefficients that contribute to the model. I would memorize that last teardrop point. Let me say that again. The penalized model only selects the tokens with statistically non-zero coefficients that contributes to the model. Boy, that sounds like that's just begging to show up on the exam. All right, let's look over at the right-hand model, actual training labels. Let's do class 1 and class 0. So that's dividend increase and otherwise. So our true positives and true negatives, what's that, 256 and 103? How about if I just round up and say that's about 360? False positives and false negatives, how about if I round up to, let's just say 30, right? So what does that give us? Nearly 400 in our model. So let's go ahead and evaluate the fit of a machine learning algorithm, right? So let's do precision and recall and the F1 score and accuracy. So you can do the math there and you get, 90%, 97, 93%, and 91%. Look at the third circle point there, consider the following confusion matrix for the cross-validation data with a threshold p-value of 0.5. So somehow I come in and say, you know what, let's just suppose that, 1 and 0, 50% chance above, 50% chance of below. So I come up with that p-value of half, and I do all of this. However, what happens is that maybe my p-value shouldn't have been 0.5. So let's just go through this example here. Model accuracy, 91.53%. That's the suggested p-value of 0.5. However, what we can do is we can impose different threshold p-values to maximize the accuracy. Remember, what we want to do is we want to get rid of the possibilities of type 1 and type 2 errors, but we have that smiley face, right? So we can't completely eliminate type 1 and completely eliminate type 2. So you have to have that trade-off. So look at the middle orange arrow point. Identify the threshold p-value that generates the highest accuracy and F1 score. So this fits really well in with that LOS up there. So without going into all of the details, but let's just suppose that we have another actual training label table like we did up in the top right, and we come up with an accuracy and F1 score of 92 and 93, precision and recall 94 and 98. So clearly we can see those are superior. So what we can say is we want to pick that p-value of 0.6. Now what we can do is continue on this. We can continue saying, all right, let's suppose that we're evaluating all of Jim's sentences and all of his structure and all of those tokens, and we can apply that now to test data. So now we can say, all right, tomorrow, right, I'm Jim, I'm gonna put something out on social media, and I'm gonna have free cash flow and toothpaste revenue. So tomorrow, that's my test data. And so I come up with this here. So actual training labels. So there's 94, 97, 93, and 92. The model performs similarly, right? It implies the model is robust and not overfitting. The model generalizes well out of sample and thus can be used to predict. So the fact that, those percentages there, the 94, 97, 93, and 92, they were similar to what we had back here, right? Not identical, but similar. Then we can make that conclusion. So what are we saying here? Look at the third one. Model generalizes well out of sample and thus can be used to predict. That sounds like a great comment, inside of this vignette. So we do all this stuff back here, we come up with these results, and then somebody inside of the team says, hey, this model generalizes well out of sample and thus can be used to predict the sentiment classes. Do you agree or disagree with that statement? And so, yeah, we'll have to agree with that. And that takes us through those LOSs. Let me just emphasize that those first four, those were kind of the basic learning stuff. This is what's out there on big data. But that fifth one there, let's apply it to financial forecasting.